Okay, then next example, we work out passive situation. Using color theory, still the same soil combination. Okay, then Kp is this value, then horizontal kpH is become 7.49. And then for each calculation, 3 meter depth, unit weight times by thickness times by kpH. So 3 meter depth is this value. 6 meter depth, contribution come from here, and then under the water table, so effective. Then thickness, kpH. Okay, so bottom effective stress, horizontal stress is this value. And water pressure contribution, so total stress, plus them together. Okay, again, we calculate whole resultant force for each area. Okay, then work out the location of the resultant force. Okay, then we work out the resultant location is this. Here, I want you to make a comparison. Total resultant for passive is this value. Okay? Then total resultant for active is this value. And here I want to say active, that means soil move, lift away the soil mass. Okay? And active, active is soil lift away soil mass. And then passive is soil move toward the soil mass. Okay, toward the soil mass, we need a very large force to make the soil move that way. Can you understand? And active is only small amount stress, but here is total force. So active is very small amount, and soil can move, lift away the soil mass. Okay, what's that mean? If we build a retaining wall here, as long as we can support it, which is enough. But if we want to make soil move that way, we need a very large force to make it move. Okay? Okay, it's also explained for passive situation, we should have a very large force. Force divided by area becomes stress. We should have a very large force to make smaller effective minor principal stress become major principal stress. Okay, so we should give additional energy to make it move. So passive is not natural state because we should push soil. Okay, and therefore, from some theoretical calculation to provide this relationship. So dense set, loose set, okay? Dense set, loose set. They use material difference to show this relationship. So positive and negative for horizontal axis, that means the movement direction. Movement direction, okay? Delta H is the movement direction. So of course, one way is positive, the other way is negative. So they use positive for active situation. So movement for that direction is positive. Movement for that direction is negative. Okay. Then compare Kp value to Ka value. You see here is horizontal divided by vertical. So Ka, you see the scale compared to K naught. So Ka is smaller. So all of them is less than 1. Is smaller. Okay, Kp is greater. Kp is greater. So again, that's the reason I prefer to remember K naught is 1 sine, 1 minus sine phi. And then Ka, because Ka is smaller. So Ka is 1 minus sine phi divided by 1 plus sine phi. Okay, and then Kp is inverse. 1 plus sine phi, 1 minus sine phi. Okay, we can remember this easily because of this relationship. But this part only, in addition, except this, these two only can be applied for ranking theory. Okay, these two. But at rest, there is no problem. We always use this one. Okay, so current theory, we finish here. Okay, current theory finish here. Right now, we talk about the third lateral pressure solution. We call as a Carpon-Kersee, developed by French. Okay, its original paper was written in French. Okay, and this method is very difficult to use simple equation to represent those terms. So mainly, when we use it, generally use maybe like table solution or chart solution to work out reasonable value. But practically, from lots of, okay, not just several, from lots of variation, Carpon-Kersee solution probably is the most close to the real situation. Okay. However, they are not easy to be calculated using equation. Okay. So not easy to be calculated using equation. In most of previous textbook, I don't know about the government exam, but most of textbook, they are ready to make this one into the content. The reason is not easy to deliver to students using theory and equation to explain this phenomenon. Okay, then for active condition, soil movement, and failure mechanism show you here. Okay, real failure surface from real observation of uniform material. Real failure surface look like this. And then from the derivation of theoretical solution, we assume like this. Remember, for ranking, we assume as a rigid body. Okay? Then for column, we try error. We try several different ways, okay, to find a solution. So our failure assume failure surface when it is close to real failure mechanism, our solution will be relatively accurate. Okay, remember in chapter 2, I mentioned when we obtain the soil's material strength parameter, the main point is we have to know reason for failure mechanism. Okay, like foundation, failure mechanism is like this. So we should get reasonable value along the failure surface, and then our design will be more appropriate. Because from our lots of geotechnical derivation and background is from reasonable assumption of failure surface, and then we derive the solution. So for geotechnical engineer, whether you have a proper judgment of failure, which is important. Okay? And ranking, they probably is no problem because most of solution for active or not ranking, for active situation, they are close now. So for active situation, the derivation probably has no big issue. However, here is a demonstration to show you for passive situation, real failure mechanism look like this. And then for what we assume the failure mechanism is like this. So it causes the difference from the derivation, okay, because our assumption is not realistic enough. Can you imagine? Because when we derive something, it's based on our assumption. If our assumption is not good enough, so our derivation is possible to be inaccurate. Okay? So Kawakasi, when they derive the solution, they consider the movement look like this. Okay, which is different from color and ranking. Okay, we go back to watch. Color, consider as a wedge. Okay? So which is not like only like last figure. Ranking look like this. Okay? So they all perform like a wedge. But realistic situation proposed by Kawakasi was okay, look like this. Okay, and maybe that's the main reason. Kawakasi solution more close, okay, closer to the real value. Okay, and then from their derivation, they consider the interface parameter and also consider equilibrium condition. But you should imagine more block equilibrium condition become more complicated using hand calculation. Okay? And therefore, not easy to use hand calculation. Therefore, they are proposed using chart solution here. Okay, that's the condition for sandy soil only. Condition equal to 0. Okay, then here consider the interface, and this for this one, there are many different figures. Okay, by considering different parameters. But for this one, friction, interface friction, consider the same as the soil friction. Okay, consider the same as the soil friction. And then the sloping surface with friction has those relationships. Okay? So again, if some value happen between interpolate, similar to foundation, like we check the bearing capacity factor. Okay, remember, this part is friction angle, but this part is Kp. Kp follow log scale. Okay, so when you check the value, you should consider reasonable estimation for the log scale. Clear? Okay, so here is 1 to 10. So roughly, okay, 1, 2, 3. Roughly middle is between 3 and 4. Okay? Roughly. So you should estimate based on log scale. Okay, and this figure is to show the consideration for different inclination of retaining wall. Okay, so positive, that's mean some value here. Okay, negative, that's mean the other side. But negative is not common. Generally, they are positive. Okay, then using Kaplan-Meier passive pressure calculation, it's possible we will apply for Kp value. It's possible we will consider a reduction, okay, due to interface friction. Become smaller. Okay, become smaller. Here, you see our interface friction. Consider they are the same, but it's possible become smaller, and practically smaller is more realistic situation. Smaller, okay, smaller. So it's possible to be smaller. So when they become smaller, we need a reduction factor. Okay, so here show you if they're the same times by reduction factor, and we can work out when the interface friction is half of friction. Okay, so if half of friction, we can apply the reduction from here. Clear? Just work out the Kp by considering a reduction factor. Okay, so here give you the procedure if Kp interface friction the same as friction, we can use figure solution shown in previous slide. Okay, then if interface friction smaller, we can use this table to work out the reduction factor. Okay, here is a comparison to show you ranking is here. Ranking is here. And color is top. And hypocrisy is somewhere between. Okay? So hypocrisy, I already mentioned, is probably the most realistic situation for real soil. Okay? So that's the reason in Taiwan, right now, for our calculation, we in industry company we always use hypocrisy. Okay? And then we calculate a passive earth pressure using hypocrisy theory. The soil is exact. Okay, then given parameter, they are the same as the previous example. And we go to the procedure and look. So Kp is 8.5. And okay, I saw here probably is typo. Here should be delta divided by 5. Okay, delta divided by 5. Am I right? No. Not 1, because they use 0.85. I have looked. 0.83. Okay, here. So should be delta divided by 5 equal to 0.2. Okay, so can you please revise this part? Delta divided by 5 equal to 0.3. Okay? Revise this part. Okay then, Kp. Sorry. Yes, correct. So Kp is 8.5 times by reduction factor. Reduction factor here. Okay? And then we work out Kp, and Kp times cosine delta. We work out cosine delta. Sorry, let me think. No. This value. So 2色 167. $33 is here. Okay, I should revise again. Because from the calculation here, so delta is 2/3 of 33. 2/3 of 33. Okay, so we know delta divided by friction is 0.6. Okay, 67. 0.67. Okay, then from 0.67, somewhere between here. Okay, then friction is 33. So somewhere between here. Okay, I just can say this value, let assess from somewhere here. Okay. So from their estimation, 33. Okay, 0.83 is somewhere between here. But anyway, for your interpolation, roughly accurate, I will consider you are correct. Don't worry too much. Okay. So reduction factor 0.83. Okay, so Kp times cosine delta. Okay, we got 6.54. And then at 3 meter depth, thickness times by unit weight times by kph. So we work out this value. 6 meter depth. First 3 meter contribution, second 3 meter contribution considering effective stress, then kph. Water pressure, and then total horizontal stress. For for passive situation. So bottom is this amount. Clear? Okay, then we have this distribution. We can work out a resultant. Okay, then total resultant. Procedurally, I will say total resultant, and resultant location calculation. Okay, clear? Okay, then for earth pressure, consider surcharge. Theoretically, we can, if the soil have a movement, Okay, so its contribution for active and passive, we can directly use that way to considering surcharge contribution. Okay, then if the wall without movement, we can consider its arrest situation. Because practically it's possible we design a very strong wall, do not allow the movement. Okay, can you get it? In practical, it's possible. Depends on how important here. I saw I forgot to mention one thing. Here, I want to tell you, this figure is ideal value. Not every soil look like this. Okay, that's an ideal value. And in reality, if the soil movement, because I see the later slide, so I remember some movement can be very small. Okay, some movement become very small. So it's possible earth pressure is somewhere between. Clear? But it's not easy to assess somewhere between. So practically we just use Ka and Kp to represent the situation. But in realistic, it's possible somewhere between. Okay, so here, we mentioned lateral aspiration contribution by line law. Okay, you just know we have this kind of thing. Line law, that means this way is infinity. Okay? Infinity. So we can use this figure to do some line law contribution calculation. Okay, and we have M value. M is this part. M value. Okay, it's a setback distance. Setback distance. Okay, and for the line load for different depths contribution, okay, they also have different value. So for the line load contribution, we can use this relationship to work on. Okay, but you don't need to worry too much. Actually, in Taiwan, most of company, if you have to derive this, they already write this relationship in itself. Okay, so of course you can write by yourself to work out this. So if it is needed, they just use Excel easily to work out the relationship. Okay, then for lateral aspiration contribution or from the strip law. So we can use this way to work out the contribution. Okay, then here is a relative special consideration. Maybe in Paraguay is not common because we should consider earthquake design. But mainly this part is postgraduate level of knowledge. So you just know we have this kind of consideration, which is enough. So we will consider earthquake contribution. So W, you can imagine is self-weight. Self-weight. Okay, then when earthquake comes, we will have certain contribution to regarding the weight. Okay, and which is the initial force come from original mass. Original mass you can also consider as your weight, your original weight. Okay, or for this considering mass. Okay, then earthquake we simplify. Okay, it's a simplified method. We simplify their contribution become horizontal acceleration and vertical acceleration. Okay, so its contribution become like this. Theoretically, these two values less than 1. Most of situation less than 1. Even I can say most of situation these two values less than 0.5. Because if we use this value too big, doesn't matter what kind of design, we cannot build this infrastructure. Can you imagine? Because too big, that means almost our design will be failed. Okay, we cannot achieve reasonable final answer. So even we know earthquake can be bigger than the value we consider, but for our construction, we should consider reasonable cost. And also, earthquake do not happen every day. So we consider reasonable time frame. We shouldn't use this value too big, and then we cannot build a reasonable structure. Okay. So theoretically, these two values will be less than 0.5. Okay. And depends on the location. In Taiwan, different place, those values they are all different. Okay. And then we use that way to consider the earthquake influence. Okay, when earthquake come, this answer derived by that's from Japanese. Okay, so we can apply this equation in Ka A active, E earthquake. Okay, Ka E. We can use this term. Okay, and alpha can be derived from here. Can be expressed from here. Anyway, this term is we work out a triangle. We work out a triangle, and the right triangle relationship. Okay, and here I want to mention for this equation. For this equation, considering failure plan look like this. So that means for our problem, the failure mechanism should look like this. And then our answer can be accurate. Okay? This solution should follow the assumption failure mechanism like this. Okay, and here I emphasize again for Kappa-Kersey. Passive theory is not accurate from Rankine and Harlan is due to failure mechanism. They are not similar. Okay. So again, if earthquake failure earthquake failure does not follow this failure mechanism, and then the answer derived from here cannot apply properly. So that's the problem. But anyway, so far we don't have better solution to consider this issue. One of the reasons could be in practical, earthquake to cause this kind of damage is not like big data to help us identify this situation. Okay, so today we finish class here, and next Monday we still have a little bit, still have 1 hour class, and Tuesday is exam. Okay, and Monday I will finish this chapter, and when you finish the exam, and Tuesday or Wednesday I will ask TA to upload the assignment question for chapter 4. Okay, but chapter 4 belong to the next midterm content. Okay? Cheer up. Don't let me feel you are tired. I'm also hungry.